Hey everybody, here's section 10.6, some more angle arc theorems. In this section, we're going to recognize congruent inscribed and tangent chord angles, determine the measure of an angle inscribed in a semicircle, and apply the relationship between the measures of a tangent angle and its minor arc. If you don't remember what a tangent chord angle is or a tangent angle, I suggest going back to 10.5, watching that video again so you do know what they are. So our first theorem for this section is theorem 89, which says if two inscribed or tangent chord angles intercept the same arc, then they are congruent. So what this actually means is I have this angle here, it's in red, angle AXB, which is this angle right here. It intercepts arc AB. How I know that is if I were to extend the sides of my angle, so just keep them going out. Arc AB is between those lines. That's how I know that it's been intercepted by this angle. Same goes for my blue angle right here, angle AYB. So let me highlight that. It also intercepts angle or arc AB. So how I know that is if I extend the lines again on this angle, arc AB is between them. So these two angles are congruent because they intercept the same arc. And how we're going to use that is here's a proof that we're going to use that theorem for. And in here we are given a circle and we're given all this information in the picture. And all we're given is a diagram as shown. So we have chords all over the place. We have centers O. But we're trying to prove that triangle VTL, which is this left triangle, is similar to triangle STN, which is this right triangle. And the one and only way that we have done that before is using angle-angle similarity. And in order to use that, that means we have to prove that two angles of this triangle are congruent. And right now, just looking at this picture, I see two angles right here being congruent based on vertical angles. So step 2 is that I have vertical angles are congruent. So these angles are angle VTL being congruent to angle STN. So there's one angle on each triangle being congruent. Now here's where that theorem we just talked about comes into play. If I look at angle NSL, which is this angle right here, if I extend SN and I extend SL, that shows me that it's this arc that's been intercepted by this angle. And if I look at angle V up here, and if I extend those lines, it intercepts the same exact arc. So that means that these two angles are congruent. So that gives me my second angle. And unfortunately, there is no abbreviation for this theorem. So you have to write it all out. But now I have angle V is congruent to angle S. So now I have two angles being congruent of these triangles. So my next line is that I can say these triangles are similar. And that is the angle-angle similarity. And I wrote that wrong. That's my fault. So that is the angle-angle similarity. And that proves that triangle VTL is similar to triangle STN. Now, the last that we want to prove is this long line right here. But before we could do that, we have to write proportions. If you remember those are two fractions that are equal to each other. And in order to do that, we have to figure out how to place these four segments in this proportion so that when I cross multiply, I end up multiplying these two and multiplying these two. So I'm going to first place TV. You can place whichever one you want first, doesn't matter. But if I place TV on top, I have to place TN somewhere on the other side so that multiplies by TV. So when I cross multiply, I multiply TV by this bottom one. So that's how I know that TN goes there. So when I cross multiply those get multiplied. So that's perfect. Now I want to put these two somewhere in here so they get cross multiplied. It really doesn't matter how you put them. So I can put TL on the bottom here and ST on top here. I could have just as easily flipped them around. But if I were to cross multiply, which I did down here, so TV times TN, that's that side, and TL times ST, that's that side. So that's how I know that that was correctly set up. Now, the reason for step 5 was a really long one that's very, very similar to CP/CDC, but we said it was corresponding, so corresponding sides of similar triangles are proportional. But we had a very nice simplified version of this that we called CSSTP. Very close to CPCTC. Same 5 letters, just different ones. And then our last theorem, which allowed us to do the cross multiplication and get this, was the means extremes products theorem. And that gave us our proportion right there. Now, before you freak out thinking that, oh my gosh, these proofs are going to be so hard, that is actually the only proof out of this whole entire thing. So it's not so bad. But we do have more theorems we have to go through. So our next theorem says that if two inscribed or tangent chord angles intercept congruent arcs, then they are congruent. So this red angle right here, angle APB, is a inscribed angle. So here's our angle, here's the intercepted arc. Here is a tangent chord angle. So here's our angle, here's the intercepted arc. So if the chords are congruent, then my angles are congruent. Sorry, so let me rephrase that. If the arcs are congruent, then the angles are congruent. So it's kind of like the transitive property that we learned before. So congruent arcs implies I have congruent angles. Theorem 91 says that an angle inscribed in a semicircle is a right angle. So the proof of that is angle B, because we know inscribed angles are half the measure of the arc. Well, if it's a semicircle, the arc is 180 degrees. So that means angle B is equal to 1/2 times 180 degrees, which is equal to 90 degrees. So therefore, angle B is a right angle. It does not matter where angle B is placed. It will always be a right angle if it's inscribed inside of a semicircle. You will need to remember that that makes a right angle, and that makes a right triangle, which is probably going to be using that lovely theorem that all of us like to use, the Pythagorean theorem. So our second example is that we have the circle R. We know that BC is the diameter, and the radius of the circle is 6.5 millimeters. We are also told that chord AC has a length of 5 millimeters, and we want to find AB. So let's put everything in here. We know the radius is 6.5 millimeters, so that means RC or BR, they are both 6.5 because they are both radii. And we're told that AC is 5 millimeters. And we want to find AB, so I'm going to put an X there. Well, based on the theorem we just learned, angle A is an inscribed angle of a semicircle. So that means this angle A is a right angle. And to find the missing side of a right triangle, we use Pythagorean theorem, which is the A squared plus B squared equals C squared. So we have to figure out what's our A, what's our B, and what's our C. Well, we got to know this whole length actually. So let's find that first. 6.5 plus 6.5 is 13. And we know that across in the right angle, no matter what it is a C. Now A and B are whatever two we have left. You may pick whatever one you want. I could have made 5A and XB. Does not matter. And I'm going to start plugging everything in. So my A is X, so I do X squared plus B, which we labeled as 5, so plus 5 squared, equals C squared, and our C is 13. So we do 13 squared. Start solving it, we get X squared plus 25, because that's 5 squared, equals 169, which is 13 squared. Subtract 25 from both sides, and we get X squared equals 144. Take the square root, because that's how you undo a square, and we get X equals 12. So that means our length from A to B is 12 millimeters. For our next theorem, we are told that the sum of the measures of a tangent angle and its minor arc is 180 degrees. So what that means in terms of this picture, is that this angle right here, angle P, because PT and PS are tangent. So this is my tangent angle, and it's minor arc. Its minor arc is this arc. So minor arc, remember, is the smaller arc. It's less than 180 degrees. So there's my minor arc. It's also the intercepted arc of my tangent angle. So whatever angle P is and whatever the measure of arc TS is, it will always add up to 180 degrees. So let's see how that works. So in this one, we are given that RS and TS are tangent segments, so that means this is a tangent angle. And we are given that the measure of arc RT is 123 degrees. We're wanting to find two things here. We're wanting to find the measure of angle S, and we also want to find the measure of angle SRT. So we also want to find this angle right here. So to find angle S, let's start with that one first. We know that a tangent angle and its minor arc have to add up to 180. So that means angle S plus arc RT have to add up to 180. So I'm going to start plugging things in here. I don't know what angle S is, so I can't put anything down for that one. But I do know what arc RT is. I know it's 123 degrees. And they have to equal 180. Well, now this just becomes an algebra problem. So I subtract 123 from both sides. And I get that angle S is equal to 57 degrees. So there's one of my answers. Now the second one is having me find angle SRT. Well, if you notice right here, length RT, that's a chord, and RS is a tangent. Based on yesterday's lesson, we know that a chord tangent angle is half the measure of its intercepted arc. So I know that angle SRT is going to be equal to half the length of arc RT. So that means that this is going to be half of 120, so I'm going to or 23, sorry. So I'm going to multiply these, and I'm going to get that this angle is equal to 61.5 degrees. So that is my other angle. So remember that a chord tangent angle is half the measure of its inscribed or intercepted arc. So let's move on to our next example. Don't panic. This picture looks confusing, but it's not as hard as it seems. So let's fill in what we know. We know that arc FB, which is this arc right here, we know that this is 120 degrees. We also know that angle E is 52 degrees. We want to find angle C, which is this angle right here. Well, I see a triangle. I know that a triangle has to add up to 180 degrees. So that means I need to find angle A. And if I can find angle A, then I can find angle C. Well, based on the theorem that we just did, I know that this angle right here and this arc right here have to add up to 180 degrees. So I know that angle A plus 120 degrees has to add up to 180. So that means that angle A is 60 degrees. See, not so hard. So angle A is just 60 degrees. And now I know angle A plus angle E has to add up to, or plus angle C, all have to add up to 180 degrees because it's a triangle, and triangles add up to 180. So we know A is 60, we know E is 52, we don't know angle C, so we're trying to find, so we leave it there. Has to add up to 180. Well, 60 plus 52 is 112. So plus angle C is 180. Subtract 112 from both sides. So I get angle C is equal to 68 degrees. So yes, it's a lot of work to find that one, but it's not as hard as you think it was. All I had to do was find one angle because I knew its arc. And I found the other angle by knowing that a triangle is 180 degrees. So let's do one more example because I know by now you're going, oh, Miss Malone, I want to be done. So last example, I promise, and then I have two examples for you to try on your own. So this is the last one we'll do together. So in this example, we are given that angle M is 7x. We are given that the arc LO, so when we use two letters, we try to find the shortest distance between them. We know this arc is, or the arc is 14x minus 9. Well, you're thinking, well, what can I do with these? I'm not given any numbers. We are told, remember, that the angle and the arc add up to 180. So I want to find the measure of angle M and the measure of that arc. Well, in order to find that, I'm going to find out what x is. So I got to set up an equation. So I have 7x plus 14x minus 9. Because remember we said these two add up to 180. So now it just becomes an algebra problem. Combine like terms. 7x plus 14x is 21x. Bring down the minus 9 because we can't combine it with anything. And that is equal to 180. Add 9 to both sides. And I get 21x equals 189. Divide both sides by 21. And I get x equals 9. Unfortunately, we're not done yet. I know we got to do more work. So what I got to do is to find angle M. So the measure of angle M was 7x. I now know x is 9, so I'm going to plug this in to get 7 times 9, which is 63 degrees. So there's one down, one to go. Do the same thing. We were told measure of LO, so measure of arc LO was equal to 14x minus 9. So again, plug it in. I do 14 times 9 minus 9. Well, 14 times 9 is 126. And when I subtract 9, I get 117 degrees. Now, don't just assume you're done now. Double check. Do these two angles, in fact, add up to 180 degrees? Always double check, because we could have done our math wrong. So let's double check. Does 63 plus 117 equal 180? And it does, in fact. So that means our answers are correct. So we are done, but before you go, I want you to solve these two problems. So take a minute. Here's example 6. I want you to do this on your own. Remember, it's a angle inscribed inside of a semicircle, so remember that theorem. And we also have example 7, which is very similar to one we did before. So make sure you're filling this out. Instead of on the paper, you are going to do a quiz on Edmodo, and I will explain that more if you need any help.